All right, here we go. This is section 4.2. What 4.2 is going to start to do is introduce more of the steps that we're going to need to do a hypothesis test. But two major things show up in this section. One of those is randomization distributions, and then the second other huge thing are p-values. Now, what hypothesis tests are, again, thinking about from section 4.1, is really just boil it down to an argument between two individuals. One of them who says they believe uh, a parameter is equal to a certain value, or that two groups have really no difference. Or the alternative is where the second person is saying, no, I think things do differ between group one and group two, and so that's what we have here. Remember in 4.1, we use the idea that we can use notation as to what the two arguments are. In this one, if you read the first sentence, this here is a study about either tea and coffee. And what I circled there is that someone is saying, well, whether you drink tea or whether you drink coffee, they're going to do the same thing in terms of boosting your immune system. But then someone else might come along and say, no, I think tea is better. That when you drink tea, it's going to have a greater effect on your boosting your immunity as opposed to coffee. Now, that's as far as we were really getting in section 4.1. But now what's going to happen is like, how do we win? How does someone win their argument? And so what would need to happen is they would need to do a sample and see what occurs or what result. So to start filling in some notes here, we're going to say that when you do a hypothesis test, something needs to be tested. You need to put it to a test to see what or which of the two arguments is more plausible. Now, when we were doing in chapter one, we talked about there being experiments, and that is what's happening on this one. So they're going to get some participants. Let me make sure I spell this right. Participants. You're going to recruit some individuals. And then what they did is for 2 weeks, they had some drink black tea and they had some drink coffee. And when the results came back, you can see these are the values for immunity boost for the tea drinkers. And you can already see that those numbers do appear to be on the larger side as opposed to those over here in the coffee side. Now, this was to see who had a greater average boost in their immunity. And what ended up happening was tea was better by about 17.12 points. Now, one thing I did do was I also calculated what the average for this was, just to give us also another way of like a snapshot of what happened. And it was 30. I'm just going to sneak it right in here, 34.82. And for the tea people, whenever their average came back, it was 17.7. And so that's where you can see roughly like a 17-point higher score for the tea drinkers. So going back to the whole argument, it does seem like that argument seems to make more sense, that if you drink tea, it's going to do better for you than what a coffee does. Now at this point, some might say, well, case closed, like, the deal is done, or we can close the book on this. But what we're going to do with hypothesis tests is start to think a little bit more about um, things happening by, either they were a fluke or they weren't a fluke. And so as of right now, what we can say is that based on the observed results, tea was better. But maybe there's somebody who's like a fighter for coffee and believes like, no, I don't think so. Like, how do you know? Like me, I really do enjoy my coffee. But what if I was to be like, no, I mean, I don't think there's a big deal. This maybe this was just a fluke. And so the fight continues on, or the argument continues on. And it could be that one of two reasons why this happened, that T was higher by 17 points, is that either it's true that there really is going to be evidence, and maybe if they were to do it again and again, that T would be better once again, Or maybe this occurrence of that 17 points being higher for T, maybe it was just a fluke. And so a lot of textbooks will use this, that maybe it just happened by random chance. But I want to throw in there the idea of it being a fluke as being sort of a more like elementary way of describing like what happened. Now, if something just happened by fluke, like let's say you did something amazing and people witness it and they're like, oh, that was just a fluke, right? If they describe what you just, the amazing thing that you just did as a fluke, that means they don't have a lot of confidence in your ability to do it again and again and again. Same thing here. If we're saying that that right there was just a fluke, we're saying that the ability for T to do that again and again and again is probably not going to happen. So the way that the argument goes on, or the way that we can show, let's suppose that we are on the side of T in which we want to have evidence that it was not a fluke. You could actually do the study again, repeat it with a brand new group of people, participants, tea versus coffee. But one of the things we talked about in chapter 3 was that by doing the bootstrap method, it's also a nice way of being able to replicate the study without actually really doing it with our own blood, sweat, and tears. And so Stacky can do that for us, and it can show us like many, many times what might happen if the study was repeated. Now, more specifically, here's what's going to be happening. And you can see it right down there. You can see what looks like a bootstrap distribution from our chapter 3. But there's a couple key things that are happening in this little dramatization of what if we were to do the study again and again, many, many times. And here's what Stacky's doing. It is taking your original sample and it's lumping it. I'm just gonna put a little circle here. It's like lumping it all back together, like all of those participants from the original like trial experiment, putting them all together and just re-randomizing them out into a brand new tea group and a brand new coffee drink. Again, inspired by the original results. And it puts into the idea that, well, what else could have happened if we just randomly mixed them up? And the one that I have here, I just put a box around it, actually comes out with a negative number, which was the idea that the average for the tea drinkers, it could be lower, right? Could be lower than the coffee group. But again, that's not actually what happened. That's just a re-randomization of like what else, something else that could have happened, but specifically by random chance. So when you look at this little diagram down here, or the randomization distribution, you're seeing what are 1,000 other things that could have happened, but by random chance. Also, under the assumption that the two groups don't really have a difference, that mu1 is the same as mu2, or in this one would be that the average, right, this right here, this little thing right here, it is suggesting that what might be true is that tea and coffee have same effect. That one of them is not going to be higher or lower than the other. And so when that happens, this is what number you'll see in the middle. That if tea and coffee have no difference, or they do the same thing for you, that's going to be a null value of 0. Now, I'm going to try to keep this not super long-winded, because if I do, I feel like it's just going to get us more on like rabbit trails in our mind. So when you look at one of these things, here's how you're going to use it. And what I might do is I might just take a couple dashed lines, maybe like, I don't know, right about here, and maybe another one right about, I don't know, maybe at this spot there. And notice what that's supposed to look like. It's supposed to look like our 95% confidence interval. And what's happening here is that those that are in the middle are most likely to have happened, because we see a whole lot of them. But the way they're described in today's lesson is these are most likely due to random chance. These are the things that most likely would have occurred if we just we're letting things randomly happen. Now, that in today's story is not good because these are the things that would be most likely just happen based off of a fluke. And again, if you do something spectacular and someone says, "Oh, that was probably just a fluke," that means that's not that they don't have a lot of great confidence in your ability to do it again and again. So anything on the outside of this would be your not fluke, or we could more specific, like less likely that it was a fluke. And notice who's here. I'm going to add the word original. That's 17.12, the thing that actually really happened. This was the observed. So we put a verse observed stat. It's on the outside of this distribution, which means probably was not a fluke. And so that's the big sort of like takeaway from this. Anything near the center most likely just happened by random chance, was a fluke. And then anything that's out on the tail, and we'll say in a little bit anything that's on either tail, but anything that's on either tail was probably not a fluke, or there's a smaller chance that it was a fluke. And that's all I'm going to say about this first page, because usually this section starts to feel just very, very like heavy on the conceptual side. And so the main thing that I want to definitely get you the ability to do is to be able to use one of these randomization distributions, knowing that it also in the background has these ideas that, first of all, the two things that we're trying to argue are not the same. And in the case, the example one is that tea is better than coffee. It's an argument. And we are going to always imagine ourselves being on team HA, trying to argue for the alternative. But if you've ever been in an argument, one of the best ways to win your argument, if the other person just really, really believes that they're right, is to go ahead and assume that they are correct. Say, okay, well, let's just assume that the other person is correct. We know they're not, but let's just assume that they're correct. Let them start telling the story of what happened, and then as they go along the story, hopefully they'll run into something that makes them realize, oh, wait a minute, I forgot about that. Yeah, I see where I'm wrong. So that's what's happening in hypothesis tests. We want to find evidence for the alternative, but we're going to assume that HO is correct. So when you see one of these randomization distributions, we're not saying that the null is true. We're assumes that the null is true in hopes that when we do a sample, we can find something that contradicts it. Now, the null value, the thing we're trying to argue against, because we're assuming to be it's true, it's going to be sitting in the middle as if though it is true. But then when we do our sample, we're going to want to get something that gets that returns a value that contradicts them. So if we get a value that's like right next to them, that's not good for us because that seems to be supporting whatever they're claiming to be true. But if we can get something way out here on the tail, maybe like right over there, or maybe like just barely on the outside of the what's going to be our cutoff line, that's a win for us. Like we found something that contradicts you, right? The further away we are from it, the more that we can say it seems to be the other person's argument seems to be wrong. And then I got little short descriptions here. Anything that happens out on the tails are going to be less likely that they happen by random chance. Maybe weren't a fluke. They give us evidence against the null to contradict them. Same thing on the other side as well. And if you're wondering why is there a left tail, right tail? Because sometimes we're going to be arguing for greater than, sometimes we're going to be arguing for less than. And when it comes to making conclusions, again, anything that's in the center would not be good for us because it would not give us evidence against the null. Victories for us happen anytime that we're way out on the tail. And because remember when we were doing chapter three, we would say, we're 90% confidence, 95% or 99. We never actually say that we're 100% confidence because things are based off of samples, based off of randomness. So the conclusions that we make, if we do find something that contradicts the null, we usually use words like there's enough evidence to support the alternative claim. Now, part of making our conclusions in these math problems that we're going to have is that there's going to be sort of a wrap up conclusion where we're going to spell out in words like what was happening. And this is what we were trying to, right? If we were on team T, this is what we were trying to prove to people, again, just to use a very strong word there, that tea was better than coffee. But this is the opportunity to recall, what was mu about? What was t about? Why is there a little greater sign there? And to the conclusion, what we would put here, like what was the study about? It was trying to argue that the mean immune boost is greater after drinking black tea for 2 weeks than coffee. That is the big takeaway that they were trying to accomplish by testing tea people versus coffee people. And it seems like they do have pretty strong evidence for that, in that the result was on the side of it not maybe not being a fluke. All right, let's keep going. Right, because yeah, this is a bit heavier conceptual type lesson. And so, again, I'm trying to keep myself not so like long winded with this, because this is going to be something you're going to need to let kind of grow on you as we go through more chapter 4, even as we get into chapter 5 and chapter 6. It's usually after about someone finishing 4, 5, and then the beginnings of chapter 6 before we start to students finally start to connect all the dots, and starts to feel like the flow of a hypothesis test like really starts to like they get to groove in a groove about it. All right, now the other big idea today is a p-value. So if we want things that are the results of a study to not be flukes, right? Or for someone not to come and say, hey, you just did a study, you just got that result, but I don't buy it. I feel like that was probably just a fluke. Thankfully, p values are a way to measure how likely something was to have been a fluke or not. And again, we don't want people, after we've done some amazing thing, to be able to say, hey, that was just a fluke. We want it to be on the smallest possible chance that it was a fluke for them to start to, maybe for us to convince them. Okay, so the smaller the p value, the better. Because again, p values are trying to show you whether something was to have been a fluke or not. Now, let's start off with just the middle p-value. So in the middle is 0.5. And so if a p-value of zero point 0.5 would be like saying, there's a 50-50 chance that it was maybe a fluke, that it wasn't a fluke. So you're just like right in the middle. But if you have a p-value that is smaller than 0.05, and what's the 0.05 coming from? It's this. That's the same thing as saying, well, you just witnessed something, and if it has less than 0.05, that's to say that it has a less than 5% chance that it was a fluke, which in the world of statistics, that's usually like our starting baseline. Anything that's smaller than a 5% chance that it was a fluke is pretty good, right? There's a pretty good chance that if you were to do the study again and again, that you're going to see that result happening again and again and again, like more often than not. Now, there's the definition for the p-value. It's mainly it's going to help us a couple things. One, get the idea of like how to calculate a p-value, but then also what it does is remind us of the way that the argument is happening. Again, the p-value happens when we're assuming that the null hypothesis is true. Not saying that it is actually true, is that suppose it is true. Okay, let's try to find a way to argue against it. But the p-value is the proportion of statistics in a randomization distribution that are as extreme or more extreme. And you'll see what that means in just a moment. Okay. So whenever you're calculating the p-value, what you're going to be hoping for is a smaller p-value, because that is going to be backing up your result as to whether it was by fluke or not a fluke. And if we start with a one-sided test, what I'm doing here is just focusing on some of the homework that's going to say calculate a p-value. And you're going to do it manually by yourself. There's going to be sometimes you do it with stat key, but then this is the version, like how do you do it by yourself? Now, the p-value, what you do in terms of procedure is you count the dots that are on the tail depending on what you're trying to test. So here they're saying suppose that this is a randomization distribution that has 500 total dots. Like from here all the way to there is 500 dots. But you don't have to worry about counting all the dots. You have to worry about counting the dots that are on the tail that you're testing. And you'll know which tail to work on because they'll do something like this. The alternative will be trying to argue in favor of a value being less than, or that group one is less than group two. Now, in order to know how many dots you'll count, you'll have a statistic, something that was actually observed when you did your participants, and you'll have that value. And you'll take that value and you'll go to the left tail and you'll just locate where it is number wise. And then right here, anything that is as extreme as what you observed, which would be anything right above it, or anything that is more extreme, which would be more to the left. And you'll count those dots. Now it's 1, 2, 3, 4, 5, 6, 7, 8. So the proportion of dots that are as extreme or more extreme out of the total number of dots that were re-randomized. And so now you can see that a p-value, when you calculate it, simply really is just a proportion, like a fraction, numerator, denominator. But then what we'll do every single time is turn it into a decimal. And so that would be the same thing as 0.016. Now, one of the things we're going to be doing is hoping for smaller p-values if we're trying to win our argument. This one here is pretty good because it's like 0.01 or 0.02 if you round it a little bit, which we won't ever round our p-values. We're just going to leave it like that. This is considered a small p-value. Now, sometimes you're going to be doing a test to see whether something is greater than a value or whether group one is greater than group two. And so you would have a value and that would lead you to the right tail. Again, you would take your statistic, whatever was observed, and you would locate it based on the number line over here on the right tail. And if there's nothing immediately right above it to count, then you just move on to anything that is more extreme, which would be to the right. So that would be 4, 5, 6, 7 dots. And again, they'll tell you how many total dots were re-randomized. And you would divide that to get your p-value. Now, my main focus here is whenever you're asked to calculate a p-value, you'll need your statistic, the thing that was observed from the sample. And you'll need to locate that down at the bottom, just doing an estimate of roughly where it's at. You'll need to know how many total dots there are. That way you can build your proportion fraction and then turn it to a decimal. Now, I want to try one here again real quick. Now, again, when you do a hypothesis test, there's many steps to it. This is just one of them. There's going to be a part within the procedure that you'll need to calculate the p-value to help you make a decision. Now, step one of a hypothesis test is to state, what the two arguments are about. So this could be one that maybe I'll just recycle the idea. Remember in section 4.1, someone had said that they believe that 30% of to go boxes at restaurants are being left behind. Well, somebody might come along and say, well, I don't think it's 30%. I think it's something less than 30%. Like maybe it's 20% or maybe it's 10%. So that would be them arguing in favor of a less than what the initial statement was. And at the same time, it would be, if we need to go calculate a p value, a less than test is also focusing on the left tail. Now, in order to win the argument, who's right? Is it 30% or is it less than 30%? They would need to do a sample and see if who the sample seems more likely to support. Now, suppose this is based off of a sample, you get p hat equal to 16%. That when they actually collected the data, that they got 60% of the to-go boxes were left behind. Now, that would immediately seem like that is more likely to be the truth, that it's not 30%, that it's something less than 30%. And so the person arguing for less than 30% would already be raising their hands, celebrating, like, haha, I showed you it's less than 30%. But then person one might say, well, how do you know that wasn't a fluke? Well, they could re randomize it many, many times and then come down here and notice that 0.16 is down there in the number line. And so you would take like a little arrow and you would put it right about below where 0.16 is. And again, 0.16 is our statistic, or in other words, what was observed from the sample. And we want to calculate the p-value for that observation. And notice that there's 4 dots right above it to count. And then there's also several dots that are more extreme or more to the left of that. And so that's what p-values are. Whenever you're asked to calculate p-values to see how likely it was to have happened by random chance, or in other words, to say that it was a fluke or not, you would count those dots up. That's going to be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of them. You put that the p-value is equal to 13, and then they will tell you how many total dots were re-randomized, and that was 500. And then you would turn that into divide it to get your p-value as a decimal. You would get 0.026. Again, this is just one step amongst the several steps that you'll be doing in a hypothesis test to help you make conclusions. Now, we're not going to be actually using the p-values to make any conclusions today. When we get to 4.3, that's when we'll put this all together. So the main thing 4.2 is doing is introducing the randomization distributions and then also the p-values, but you're going to see these get incorporated into the bigger flow of hypothesis tests. Now, I do want to start trying to build the full picture for a hypothesis test. So let's look at this next example. Example 3 says that Paul the Octopus is famous back in 2010. It was that the World Cup soccer was going on, and he was asked to predict who would win out of 8 different matches. And the crazy thing is he got a perfect score. He was able to predict 8 out of the 8 matches and who would win correctly. And I believe what they did is they put like a bucket with like the flags, like both of the two teams, and he would like pick whichever bucket, and but he got 8 out of 8 correctly. Now, as we saw last time, you can do hypothesis tests for all kinds of things, and so you could put this to a test. There could be someone who says, he just got lucky. He's not going to be able to do that all the time. But there could be someone who says, no, like maybe he has some sort of like psychic powers. And so this could be put to the test. And again, there's the word test. That's going to be a great, great trigger word for helping you identify in your homework what the HO is and what the HA is. Again, these are the two arguments. So the test is to see whether Paul is able to choose the winner correctly more than 50% of the time. And so this is a continuation of 4.1, where remember the HO always uses the equal sign. And maybe Paul doesn't have any special powers. Maybe all he's able to do is guess and get at least 50% of them correct. But someone might be saying, no, I believe he has, some sort of extra sort of power and he can get more than 50% of them right. And so this is our hypothesis test. This is our two arguments. He can only do as good as 50% guessing correct, which maybe you and I could maybe guess 50% of them right on a good day. Or maybe he's got psychic powers and he can get more than 50%. Now, this is what we didn't do last time a whole bunch, but now we're going to start doing it. We're going to go ahead and look at the sample to see which of the two arguments the sample most likely supports. So for part B, it's going to say observe sample. Right? Calculate Paul's observed sample, use correct notation, which since it was a proportion, like how many out of a total, we'll use p hat. He got 8 out of 8. But as a decimal, which we're going to be using decimals a lot. So we're going to start off with the fraction, but we're going to switch to the decimal. He got 100% correct, or 1.0. Now, to get the p-value for that, you're going to take the 1 and look at the number line here. And look what's in the middle. First of all, what's in the middle is 50%. Then maybe it's true that he can only get 50% of them right. But let's see if we can contradict that. And if you look at the bottom right corner, you can see that they've got 0.8, 0.9, 1.0. And we're going to put our little arrow right here because that was the observed statistic. And so to calculate the p-value, you're going to count how many dots are that extreme or more. This is pretty straightforward. There's only one dot there. There's nothing over here to the right to count. It's just the one dot. But all the dots that you see, they'll let you know either right here is a good spot to see it. There was 200 dots that were re-randomized. They'll also say it right here. Those 200 dots that were re-randomized to see like what else could have happened by random chance. And Paul is only 1 out of 200, or his result is only 1 out of 200. And so you would divide that to get his p-value. Again, we're not going to do anything yet with the p-values. They're going to be part of helping us make a conclusion. I mean, spoiler alert here. Anytime that you get a p-value that's really small, like this one here is really small, like 0.005, would be that what he did was most likely not a fluke. And again, would be arguing in favor of this. All right. That was not a fluke. He most likely would be able to do that again and again and again. And so whenever we say we're doing our wrap-up conclusion, it's usually to restate what that was trying to argue for, which is that Paul can get a proportion, the proportion of correct guesses that he gets is more than 50%. That'll be our conclusion in context. So Paul, again, all we're doing is just restating this, that the proportion of correct guesses is more than 50%. There's evidence that Paul can choose the winner correctly. 50% of Now, unfortunately, if anyone happens to Google this or wondering like, what did he ever do it again? Unfortunately, no, he did pass away later that year. But I think as a tribute, Paul should be the mascot for statistics. All right, well, let's keep going. Let's try some other ones here. Um, Now, in 4.3, we're going to do a few of these hypothesis tests, like from start to finish. Right now, it's still mainly us trying to like put the pieces together. One of the other things to have a heads up on is that there are sometimes that we're going to be doing a two-sided test. And so what I mean by that is that usually someone, whenever they're doing a hypothesis test, will have kind of a hunch whether things maybe are less than what the first person stated or maybe greater than. Like if someone says, hey, I think college students are getting 7 hours of sleep, I think a good chunk of us would probably come and say, no, I think they're probably getting less than that. But if it's ever that someone wants to challenge and they're not really sure whether they want to go left, like less than, or if they want to go right side, which is greater than, and they're not sure which way to go, then they can just stay with, I'm just going to go with, there's a difference, right? That things differ. And if they do go that way, they haven't made up their mind to go left, strictly left tail or strictly right tail, then that's a two tail test. And the main thing that's going to happen here is that whenever you get your p value, to get your p value, you'll need to double it. Because again, you haven't decided whether you're going just left tail or just right tail. You're just saying, one of those two. So in this example here, we're going to see that happening. Now, again, go ahead and pause the video. And what I want you to do is, before I spoil it, put a little box around the word test and see if you can write. Hopefully, you've done your 4.1 homework already. I definitely recommend doing that first before you start going more into 4.2, 4.3. Is that something is being tested here? This is going to be about two different groups. Your HO always uses the equal sign, but see if you can write what the HO and the HA for this would be using parameter notation, right? Using whether it's mu's or p's, less than, greater than, differs. And the other thing I want you to do, maybe before I ruin it, is also do part B, which part B would be what did they actually observe? Like what happened for the first time around, what happened the second time around, what were each of those proportions? And then if you were to subtract those, I'm just going to put right here in the middle of my page. If you were to subtract those two values, what would be the difference between the first time that they collected data versus the second time they collected data? All right, and here it comes. So this study, and again, pause the video if you still want some more time to kind of hash this one out, at least part A and B on your own. But here it is. So they were checking to see whether there's been a change in the proportion of people who say that they would favor the death penalty for someone convicted of murder. But they did it twice. They collected data in 1980, and then 30 years later, they did it in 2010. And you could see that there was a difference, right? It went from 0.67 down to 0.62. And so someone wants to test to see whether there's enough evidence to say whether there's a difference. I'm just going to underline. They want to check to see whether the proportion of those in 1980 differs from those in 2010. And this one also helps us out. They say use P1 for 1980 and use P2 for 2010. So maybe there was no change. Now we can see that there was a change, right? There was somewhat of a change, But then here we would do that maybe they do differ, which that right there is the idea of a two-tailed test. That there no one is coming along and specifically saying that it was less than for 1 year or was greater than for 1 year, just saying that it's one of those two things. They're not the same. Now, what actually really happened when we do the notation, we would do p hat 1 minus p hat 2. This is sample proportion minus sample proportion, and it was 0.67 for 1980 and 0.62 for 2010 for a difference of 5%. Now, to try to keep the flow of like hypothesis tests, so the 5% is arguing that, yeah, they're not the same. One of the groups was higher by about 5%, or you could say it's the other way around. One of the groups was lower by 5%. That's the observed statistic. And that is what we want to get a p-value. Because someone might say, well, that's only 5%, not really that big of a difference. But statistically, we can look to see whether this was a fluke or not. And so you'll take, in order to do the p-value, you're going to take 0.05. And you can see here in the middle where it's saying that there's someone is arguing, saying, no, there's no difference. But then down here, again, I want you to put a dot where about you think 0.05 is. And it's going to be somewhere right, just where, like, split the difference between 0.04 and 0.06. Again, some of us might put it right here underneath that tall stack. Some of us might put it like right here where those little two dots are. Some of us might put it right here in the middle. And that's actually where I ended up going. But if you ended up going maybe a little bit more to the side there, or maybe only on these, the counting 4 extra dots is not going to hurt anything. So yeah, so it's okay if you and I are a little bit slightly different on this one, but I would have nothing to count there, but then I would have 5 dots to my right to be able to count. Now, this would help us get the p-value, but keep in mind, since this is a two-tailed test, when we do the p-value, you would have the 5 out of however many total dots there are. Right there, they tell us that there's a 1,000 of them. But since we never decided whether we wanted to do strictly greater than or less than, we're saying it's either less than or greater than. So you need to make sure to do times 2 to double this. Now, that's when we work this out. You can do it either way in your calculator. You can either put the like do the decimal first and then do times 2, or just put the whole thing in your calculator and you're going to get 0.01 for the p-value. So this is really good reason also again why to always check the answer key for the homework. That if you were to come and you would be like, wait, why is my p-value seem smaller? It could be what's one of these two tails, and you have to make sure that you double uh, your count to be able to get the full p-value. Now, this is the way the textbook does it. They just count one side and they do double. There are some students who maybe you go to the learning lab or you get some tutoring and they might do it another way, which is this way. I'm going to do it, but I'm going to take it off. Is they count where positive 0.05 is, and then they count where negative 0.05 is. So like the other tail, and they do it this way. So they just count the dots on the left side, the dots on the right side. That would be the same thing as doing both tails. But then in that case, you wouldn't need to do times 2 since you already counted both tails. But I'm going to take that off. Again, that's just totally optional. Again, most of the students and myself find ourselves just doing it the way the authors would do it. And so you'll see some of these two tails pop up every now and then. Now, the last thing that we're going to do is a way to see how stat key can be used to also help us get the p-values. This one's already set for us. This was a study that they were doing to see whether students could do better memorizing words, whether they took a nap or whether they would rely more on coffee. And you can see that the hunch here was that maybe if you took a nap, you would do better than people who were doing caffeine. Now, the actual result is here. Whenever they did napping, how many words that they could memorize versus those who were doing coffee, it was better by 3 points if you took a nap. So being rested maybe is better. But if there's anybody who's like, no, 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 I think that was maybe just a fluke. How do you know that necessarily getting more rest is better than caffeine up? We can take the three and we can actually go to Stacky and see calculated p-value to see where it was maybe more of just a fluke or not. So here's what we're going to do. We're going to go to Stacky. Homework would do the same thing. It'll let you know what the name of the data set is and where we're going to go. We're going to go to the randomization test for a difference in means. Now, because this was arguing for greater than, we're going to be using the right tail. So anytime you do greater than, you're going to be focusing on the right tail to go count your dots. But this time, it's not us that's going to be counting the dots. This is going to be our statistic or the observed statistic. And that's what we're going to be using to be able to count where we want. Tell Stacky, hey, we want you to count the dots from 3 and anything bigger than 3. All right, so let's do it. Sleep, caffeine, words, difference in means. Let's go to Stacky. And right now, this is no different than having a bunch of re-randomized dots. This is our now chapter 4 stuff that we're using. And you see one that's doing a test for difference in means. And the reason why we're using this one is because those two groups, that was the average that they would memorize whenever they were taking a nap. There's the average for whenever they were doing caffeine. And then you're going to go down to sleep. Should be here. There it is, kind of towards the bottom. Sleep, caffeine, words. And then once you go into here, you'll see that's what they said the result was. 15 versus 12, but I'm going to zoom in on the main thing. We need that 3. We need Stacky to count the number of dots that are as extreme as 3 or more. So what you'll do is you'll generate 1,000. And that's usually what we'll always do for the homework, just generating 1,000 when we're doing bootstrapping, when we're re-randomizing. So the 1,000 dots that just showed up are all inspired by the original of like what else could have happened if we did it many, many, many times. But these all happen primarily by random chance. So what you'll do now to get the p-value is click the tail that you need. We need the right tail. And immediately it starts to count some dots. And it gives you an immediate p-value of 0.025. Now, I'm glad it happened to me. It doesn't happen to everybody. But sometimes, notice how at the bottom, it already has a 3 there. But Stacky will sometimes do this, not knowing that that's actually what the observed statistic was. And so it won't immediately update the count appropriately. So what you always need to do, whether it already put the statistic down at the bottom or not, is always go ahead and click on the bottom box. So if yours is showing something like 2.99 or 3.01, it's actually kind of better because you see that you need to fix it. For me, it could almost like give me the impression that, oh, it's already done. So watch, I'm going to click on my 3.000 and I'm going to manually put in there to be real specific to Stacky. It's almost like me saying like, hey, I want you to make sure that you're really doing 3.0. And then I'll hit OK. And then boom, that's better. Yeah, the reason why I said that that's better is because I can now see that it's updated the p-value. Now it's not a huge difference, 0.02025 point versus 0.027, but sometimes it'll be way off, right? The p-value would be something completely inaccurate. So anytime that you start, and I'm going to do it again, like that would be my p-value there. I'm going to do it again. Just going to reset the graph. Let's say I just do like 1,000 and I do my right tail. Oh, you can see it did it again. So yeah, it's always going to default to 0.025. So if you're doing your homework and you get a p-value 0.025, be cautious about that. It might not be your p-value. So you just always want to make sure you click down at the bottom and that you always manually update it yourself and not just leave it up to Stack and assume that it counted your dots correctly or not. Yeah. Now, the other thing that you might also, for some of us, notice is that right now it's counting like entirely that first column and then everything to the right. If it doesn't perfectly count your first column the way that you think that it should be, that's okay as long as you manually put it in. Now, my p value is 0.032. Again, we will not be getting the exact same p value because of the randomness. But I'm going to go with that one, 0.032. And I certainly don't want anyone to feel like they have to keep redoing this again and again and again and again to try to get the same p value I have in the answer key. I want you just to, again, just trust the procedure. I got 0.032. And let's say the answer key was like 0.024. That's fine. Right now we're just kind of warming up to p-values and how to calculate them. And as long as yours is similar, that's fine. Now I want to do one more last example, again, using stat key in order to help us calculate p-values. But I want to do this time something that's based on a proportion. Again, someone might be arguing saying, hey, the proportion is only going to be 50%. But then someone else comes along and says, no, I think it's going to be less than 50%. And then right here, when they actually do a statistic, they actually get a result of 0.10. So we'd be going over to the left tail, again, less than left tail. But that observed statistic is what we're going to be wanting to find the p-value for. Like, was that a fluke or was that not a fluke? So we're going to go to here, randomization test for single proportion. Lucky number 7 is the data set. All right, let's see what happens. We're going to go to test for single proportion. And again, you'll do this on some of your homework where you'll need to use stat key. And then we'll go to the data set, lucky number 7. It's about a little ways down. And there's what actually happened when they were having individuals pick their lucky numbers. Usually it's going to be a nice even distribution where 10% would say the first number, 10% the second number, 10% the third number, and so on. So those 10% who pick 7 as their lucky number, and this is what we want to get a p-value for to see whether it was a fluke or not. So you'll do likewise, you do 1,000, re-randomize. What else could have happened by random chance? And then you'll do your left tail because we're doing a less than. And look right there, I'm not scrolling all the way down, but you can see right here that the default p-value of 0.025 shows up, but that's not accurate because if you look down at the bottom, where on my screen you can see that it's counting the number of dots for 0.230. So this is actually I appreciate this example right after our last one, where the last one it seemed like it was immediately putting our statistic down at the bottom, but this one no. It just defaulted to the generic 0.025 p-value. It immediately starts counting something. So what I need to do, what we all need to do every single time is right here, click where it says, where it starts counting and change this. Just clicked on it. And I'm going to switch it to 0.10, which is what was actually observed. And click OK. And boom. Now it's doing things right.
Yeah. So it's not that stack keys doing anything wrong. It's just it defaults immediately to counting something for you. And sometimes it happens to count exactly what your statistic was, but it doesn't update the p-value correctly. So it's always just best. Moral of the story, it's always just the safest best thing not to just assume that stack key happened to count them correctly for you. It's counting it for something. But you want to just always click on the bottom left or the bottom right, depending on whether you're doing less than, greater than test. But right now, there's no dots for it to count. So the p-value is floating right above 0.000. Now, again, whenever you do any of these stack key examples in your homework, always make sure anytime, 100% of the time that you use stack key for a part of your homework, that means that there's going to be some sort of graph or image to submit in order to get your credit for that problem. So yeah, that would be a p-value 0.000. And just I'll see y'all again for section 4.3. And what we'll be doing in there is putting this all together. All right, have a good one.